So the last topic in the introduction, I think we'll be able to finish it today, is some review of probability. For some of you, this might be really quick. For some of you, you might want to go back to look at it a little more detail. And I will try to provide a comprehensive overview of the things that I think matters the most, like the probability material that you need to know for this course. So first of all, we talked about petition already, but let me give you the formal definition really quick. So if you have a collection of sets, H1 to HK, to be a partition of another set, curly H, if two conditions. The events are disjoint, meaning that there's no overlapping between any of the events. And then the union of all of the events, which is the collection of the sets, is the curly H set. Right? So that's why you can see that the union of all of the HK is H. Okay? Do you have like a quick example of what you see in petitions in addition to, I guess, what we talked about, like whether you have cancer or not? These are two events of petition of all people. Anything else you can think of? We see a lot of petitions in life. Anyone? What about the 11 values that we set for P earlier? It's a petition, right? It's a particular assumption that we think only 11 possible values are for P, right? And then we specify 11 of them, right? Okay, yes, so that's another example, and I'm sure you can come up with others later if you want. And then given the petition example or petition idea, suppose H1 through HK is a petition of curly H, and then the probability of the entire H is 1. So there are three particular things that we're about to talk about, and they're all stem from the axioms of probability. Okay, so first of all, it's the rule of total probability. So because H1 through HK forms a partition of curly H, then the sum of all of the HK, probability of HK should be 1. Okay? And that's exactly what we were doing earlier with the demonstration. Remember, we came up with 11 different values of P, and I asked your opinion about your choices of the value of P, and it should sum up to 19 because that's how many people in the class, right? And then I divided by 19 with each of the count, and then I will be able to come up with the probability of each value of P, and it should sum up to 1. Okay. Another thing, which is what we have already seen in the breast cancer screening example, is the second bullet point, is the rule of marginal probability. So here, E, it's some specific event. So if I want to know the marginal probability of the event E, what I can do is, if I can, based on the partition H1 to HK, if I can get the joint probability of event E with each element or each event HK, then if I sum up over all of the joint probability, I will get the marginal of E. Okay? And then further on, remember, the joint probability should be the marginal times the conditional. And that's what we actually saw previously for multiple times when we looked at Bayesian. To give you a quick demo, suppose I have a partition of 3 events, okay? H1, H2, and H3. Okay? Now, I want to find out probability of another event. Right? Let's say the event of this circle, which is E. Okay? So what would you do? Based on the rule of marginal probability, you will, first of all, get this part, right? That's the intersection of E and H1. And then you get the intersection of E with H2, and then lastly, E with H3. Right? And then the sum of all of the joint will give you the margin of E. Okay? And this only works if you have a partition. And that's why it's important that when we work with Bayes' rule and then try to come up, say, the posterior probability of the woman has cancer, given that she has the first test positive, we have to make sure that we form the partition right. And it's lucky, I mean, it's an easier, simpler case to do because the partition only has 2 events, whether you have cancer or not. And that's what we saw previously. All right. So the last point is Bayes' rule, and we are pretty familiar with it right now, I think. And Bayes' rule is the reverse conditional, remember? So now we have the marginal of E, and we were asking questions about the reverse conditional probability. Given the event E, what's the probability that you have one of the partition event Hj? So Hj is one of the K elements that you start with. So what you do, from Bayes' rule, this is what we know, right? And then from the rule of marginal probability, we are able to express the marginal distribution or marginal probability of E in terms of this summation. And that's exactly what we did with the breast screening test example. Okay. The larger the partition, the more computation you would do. So as you would imagine earlier with the all-nighter example, for the denominator, we have to do 11 different sums. Right? We have to sum up 11 different joint probability. And then in order to get the 11, because we have 11 values for E. And then for each of the 11 values, we have to have the prior and then the data model. So that's why it's more straightforward to do it in R, because in a loop, you can do everything all together. But if you want to compute by hand, it's not infeasible. All right, so that's the key of partitions and probability, right? So another thing important to know is, remember, we start with a partition, K different disjoint, hypothesis, or events. So now you come back with data, right? That's the event happened. And now, how can you evaluate 2 specific and disjoint, obviously, hypotheses given the data? Okay? So this is what we call trying to get the posterior ratio. So you can see that on the top is the posterior probability of one event, Hi, given E. And then in the denominator is Hj, given E. And the calculation that is being performed over here is strictly following the Bayes rule. Okay? And as you can see, this will get canceled out next step, right? So let me show you steps afterwards. So I canceled it out. And then it's important and useful to actually break this into 2 parts. So you will see that it's a ratio of what the data model follows, the ratio of that over the ratio in the prior. Okay. So typically, we call the ratio of the data given to hypothesis as something called Bayes factor. And this breakdown happens naturally because of Bayes rule. Sometimes people like to use to make decisions. I don't think we're going to use this extensively throughout our semester, but it's still a useful and important concept to know about. And this is specifically useful if you're trying to compare hypotheses after you conduct your Bayesian analysis. And by comparing, we mean comparing their posterior probability. Okay? And then because they come from, the 2 disjoint hypotheses come from a partition, then we're able to simplify this into Bayes factor multiplied with prior groups. All right. And based on this, you will see that Bayes' rule does not determine what our beliefs should be after we see the data. It tells us how they should change after seeing the data. Okay? So that's important, especially useful to see if you're breaking the comparison of the hypothesis, the ratio in their posterior, into Bayes factors multiplied with prior beliefs. And that's also, I think, is reinforced by what we just saw in the R demo. Remember when we were looking at the posterior probability and the prior probability comparison for different values of P, right? So P, I remember 0.3 starts pretty high in the prior, because majority, I should say majority, 7 out of 19 of us think that's the probability, like that's the value of P should be. But then, because the data tells us, ooh, there should be higher percentage of that happening. And then Bayes' rule and all of this Bayesian inference is telling us how our belief should change after we see the data. Okay, and this, again, might be a little bit tedious, but it's useful to just go over some of the basic probability about univariate random variable. So first of all, we start with the cumulative distribution function, CDF, that's defined for continuous and discrete for both. And then in the table here, don't worry writing down each of them. This is posted online, but certain features we need to make sure that we understand. So for the PDF of the discrete random variable, it would just be the probability at that point, right? Whereas for the continuous, it's not particularly at that point, but it's defined at the range. Okay? And then the PDF is the derivative of the CDF at that point. So that's what you should have known from your probability course. Well defined for the discrete case is summation of all of the probability that each value should sum up to 1. And that's a summation, whereas for continuous, it should be an integration. CDF is defined again through summation because it's at a particular point, but summation of all of the x until that point. Whereas for the continuous case, we first of all, so at that particular point, it should be an integration from negative to infinity at that point, and then the PDF is a differentiation of the CDF at that point, right? And expectation, this is more just a form for discrete case, it's all summations. So it's the value times the probability, sum up over here. And if you have a function of x, then it applies similarly, okay? Whereas for continuous random variable, the expectation is the integration. And then if you have a function gx, it works in a similar way. So some of this we'll use throughout the course, and I'll list them here early on. So also, as you can see, that we were talking about joint probability a lot. So once we move to the Bayesian modeling, you will see that we're going to start talking about joint distribution a lot as well. So here's just a quick review. If you have two random variables, discrete, both of them discrete, then the PMF is each at its own point, the probability of that. And then for continuous, now instead of interval, it starts to become a two-dimensional range. Where you're looking at the PDF at that point. Okay, so that's the PDF, the joint PDF. For marginal, both of this works in the same way. For discrete, if you want to have the marginal of random variable x, you integrate out y. Or I should say you sum over y for the discrete. And then for continuous, you integrate out y. For random variable y, for discrete case, you sum over all of the x. And then for continuous case, you integrate out x. Okay, so this, again, are things good to review because you might use it pretty often later on. And for the joint CDF, I leave it over here. All right. And then comes to the conditional distribution. So we start from the marginal and then get to the joint. And the next step is obviously the conditional, because in Bayes' rule, the formula that you've seen, you can guess that we will use this pretty often. So the conditional of x given y is the joint of x and y divided by the margin of y, okay, in terms of distribution. So joint density, you can also get it two ways. And remember, it is exactly these two ways that we're able to use Bayes' rule, right? It's all about conditional probability, joint and marginal, and then vice versa, which one that you're trying to get. Okay? So in the sense of distribution, that works the same. So I left a hint for a homework question later, so you can go back to this slide a little bit later when you're working on that exam, a homework question. But I also want to talk about conditional expectation and conditional variance. So those are also useful formula to keep in mind. I would recommend you to maybe write it aside on your notebook and then refer it whenever you need it. So one is the law of total expectation. Okay. And then also for the total variance. And there is a super useful formula for that. Okay, so in the interest of time, I won't go into the detail of deriving them, but this should be something that you already know from your probability course. Okay, pretty much the last topic that I want to review here is transformation of variables, which we actually will use pretty often in this course. And the general formula for doing transformation of variables is, suppose you have x as a continuous random variable with PDF fx, and now you have a function gx. You know that it's monotonic, increasing or decreasing, and also differentiable. Then you're able to use this formula to get the PDF of y. Okay? So these two conditions are actually something you need to check. Okay, I list them over here because once you have these two conditions met, you're able to get the PDF of y through this formula. But these two are necessary conditions for you to use this tool. So you can also more rigorously express it. And let's use this formula really quickly to apply for a specific example so we know how to use it, okay? So let x to be a uniform random variable, and we have a transformation of x, which is like this. So the function g of x is negative log x, okay? So now I tell you that x has uniform distribution between 0 and 1. I asked you to get the PDF of y, which is negative ln of x. And I put the two conditions here, as well as the formula that you can use. Okay? So if you play with it a little bit, maybe for some of you this is long memory long time ago, but it's still worth going over at least one example, I think, for us to make sure that we all know how to do it. So x is uniform 0 and 1. So fx is 1 between 0 and 1. Okay. And we have y to be negative ln of x. So from the formula, you see that you need to get dx over dy. And also get that express fx. And then you get PDF of y. I will wait for 1 minute to let you think through and then walk through it as a whole class, and then we're going to continue. In order to get dx over dy, you have to express y in terms of x, and then take the derivative. So y is negative ln x. How can you express x in terms of y? You confirm that x is e to the negative y, okay, once you do the transformation, okay? So express x in terms of y, and of course check the two conditions. In this case, both are satisfied. Then you get dx over dy, which is calculus. Don't forget the negative sign, okay? But in the end, you're going to take the absolute values. It wouldn't matter that much, but still, it's important to get it right. And then lastly, because fx is 1, because it's uniform between 0 and 1, right? So the PDF is 1. And now you have the absolute value of dx over dy. So that gets your PDF of y to be e to the negative y. And it's also important to remember to report the range of y as well. Because now you are trying to give the complete information about the PDF of y, so that includes the PDF itself and also its range. Okay? I will assign one more homework question on a different example, so you can practice, but make sure that you enhance your practice of this. Okay? And if you know about exponential distribution, this will be, and yeah, sorry about the blocking. Yeah, y should follow exponential distribution because all right. So the last part is something we call independent random variables. So the last part for the review. So suppose y1 through yn, there are random variables, and then theta is the parameter describing how the random variables are generated. So we have this definition of conditionally independent of a given theta for all of the y1 through yn if you have this particular setup. Let me show you. So that's the definition, but more importantly for us to remember is this part. You will see that throughout the semester, we will have a lot of probability models that is based on the assumption that the observations are IID, independently and identically distributed, okay? And that's usually what you can use, because if they're IID, and then you will be able to get the joint density of all of the observations by the product of their model. Okay? So that will be something that we'll recursively use when we start talking about Bayesian inference models. Okay? So this is good to keep in mind, and start to think about theta as the parameter in the model that we're going to give for y. Okay? So for the binomial case, theta will be p, which is the success probability, right? And then this particular PMF will become n choose y times theta raised to power of y, and then 1 minus theta raised to n minus y. So those are, we have seen it before, but this is more generic results, useful to remember. Yeah, sorry about the blocking. I'll make sure the next time it doesn't happen, but down here, I wrote conditional independent and identically distributed, so that's what you usually use to express your model. One last thing is about the exchangeability of those events. Let me show. Yeah, let me just talk about this over here. Because when we start talking about IID, a lot of times we're also making the assumption that the events or the random variables are exchangeable. So we will see this, I would say, in more detail in the lectures to come. But I do want to mention this early on, that if you have a joint distribution of all of the random variables y1 through yn, through, I should say, in this form, this will be the joint distribution. And formally, we have to define a permutation of the orders, or the indices, I should say. And the exchangeability, meaning that no matter how you're moving around the indices, the joint distribution doesn't change. Okay. And if you think this in terms of this, so remember, this is what we saw if you have IID, right? And then with exchangeability, you are able to extend the methods even further. Okay. So these are things good to keep in mind. But most importantly, I will urge you to review if you have any doubts, especially about earlier, sorry, over here, how to do change of variable, because a lot of times you have to do it in Bayesian inference. And then when you get the chance, review a little bit, let me get there quickly, of, yeah, those especially like the conditional expectation, conditional variance, those formula, review those, and as well as all of those features or criteria of random variables and joint distribution. Okay, so this, again, will occur multiple times throughout the semester. But I will also always refer you to this when we get to those points. It's worthwhile, I think, at the beginning to do this. Okay. All right, looks like time is up, so we're going to end here today. Sorry about the beginning. I hope it doesn't take too much of our time. What I'll ask you is finish the surveys as well as the, make sure that you create your data cam account, because I do want to assign some programming modules for you to brush up your skills as soon as you can. And I will also post the homework, first homework soon, later today on Moodle, so you can start thinking about it. Some of the questions are from the introduction. And then on Thursday, we will start talking about how to do Bayesian inference for proportion. It will still be very similar to the binomial that we saw, but in a more systematic way. Thank you.